Relative velocity, type 5, rivers and currents. So normally when we're looking at rivers and currents, if we want to look for shortest time or shortest distance, we have two different routes to take. So for our shortest time, we generally head straight across the river and the river pushes us down the stream. And if we want the shortest route, then we generally head upstream against the current, and the current pushes us straight across pushes us down, which leads us to end up straight across the riverbank. But we have to be careful. Is the river travelling faster than the person rowing against the current? So in this case, we can see that the man can row the boat at 3.2 metres per second in still water, and the river is flowing uniformly at a speed of 3.6 metres per second. So when we have the river travelling faster than the man will end up slightly downstream. Now we can also see this in the question because it says find the two possible directions in which the man could steer the boat. So when we have two possible directions, that generally leads us to the fact that we're going to end up with the ambiguous case for the sign rule. So let's have a look at a diagram, what's going on here in the question. So we know that the river is 45 metres wide. So we know this distance across is 45 metres wide. We know that the man is going to head upstream and is going to end up being pushed downstream. So this is the velocity of the boat relative to the river. And then our river is coming downstream, so it's going to end up pushing the boat down. And of course, we could end up across, but of course the river is still pushing us downstream. So we're going to end up slightly downstream. Which would be the velocity of our boat. I'm going to mark in the different angles we can have. So this is the direction in which the boat could set off. We have beta, and then we have C. Okay. Now we also know that the boat is going to end up 25 metres downstream from his starting point, which is why I've divided this triangle into two parts. So I know that this distance from here to here is 25 metres. So therefore I can use that information to work out this angle here, alpha, because again you can see I have the two opposite sides of the bank are horizontal lines, and the vector that I've drawn here for the velocity of the boat creates a transversal. And of course, if we have two parallel lines and a transversal, then we have alternate angles. So therefore, that's going to give me this angle here to be 45 degrees. So if I take that out, what you'll see is we have 25 metres downstream, 45 metres across stream, and across and downstream makes an angle of 90, which means then that angle there is, sorry, I shouldn't say, did I say 45 degrees there in the diagram? I didn't mean to say 45 degrees, I meant to say 45 metres. Sorry, delete that from your diagram. Hope you have marked that in. Or you should have copied that. That shouldn't have said 45, it should have said alpha. It's 45 metres. So of course, if I mark in at my diagram opposite and adjacent, it's clearly going to be tan alpha will equal our opposite over our adjacent. And therefore, we have tan alpha is equal to 45 over 25, which means that alpha is equal to tan inverse of 45 over 25, which gives me east 60.95 degrees north. Okay, so we have to look for the two possible directions in which the man could steer the boat. So he's going to, of course, steer the boat upstream. So we're looking for the angle C. And there are two possible directions because we have the ambiguous case. So why do we have the ambiguous case? Well, let's have a look at the whole overall picture. So if I was to draw my triangle, well, we've just worked out that this angle here is 60.95 degrees. I know the velocity of the boat relative to the river is 3.2 meters per second. And I also know the velocity of the river is 3.6 meters per second. So therefore what I have is I have an angle, that's the non-included angle. And also this non-included angle is opposite the smaller of the sides. So therefore, if I'm looking for an angle, so I'm going to need to find this angle here, beta, in order for me to find C. So if I'm looking for an angle, therefore it must be the ambiguous case for the sine rule. Because you have to remember, obviously, that sine is positive in the first and the second quadrant, and therefore angles obviously can only be in the first and second quadrant, and therefore because sine is positive in the first and second quadrant, we can end up with two angles, an acute angle and an obtuse angle. Okay, so let's call this our side A, angle A, and I'll call that side A, and this is angle beta, so I'll call that side beta. And we're looking for the angle beta, so we're going to go with sine B over B is equal to sine A over A. And of course, your sine rule is page 16 in your maths tables. And you can write it as B over sine B equals A over sine A, it doesn't matter. But because I'm looking for an angle, I tend to write the angles on the top. So we have sine B over 3.6 is equal to sine A, which is 60.95, over 3.2. And therefore sine B is equal to 3.6 times sine 60.95 degrees over 3.2. And then if I get sine inverse of all of that, so 3.6 times sine 60.95 over 3.2. Well, what that gives me then for the angle, I'll call it that beta in my diagram. So beta then gives me 79.57 degrees. So that would be the acute case. So of course, because there are two possibilities, the second possibility is the second quadrant. And the second quadrant rule is always 180 degrees minus theta. So of course, beta could also equal 180 minus 79.57 degrees. So beta could also equal 100.43 degrees. Now we're not interested in beta though, because if I go back here, I'm looking for the two possible directions which the man could steer the boat. So therefore I'm looking to head upstream. So I'm looking for this angle here, C. So I have beta, I have alpha. So of course to get C, I can see it's a straight angle. So I just simply subtract beta and alpha from 180 and I'll get my two values then for C. So therefore we say C is equal to 180 degrees minus alpha plus beta. So the first possibility I could have for C is 180 minus 79.57 degrees plus 60.95, which gives me that he could head west 39.48 degrees north, or we could have 180 degrees minus 100.43 degrees plus 60.95 degrees, which gives us west 18.62 degrees north. So there are two possible values for our angles. Now, of course, we're also looking for the times in which this can occur, so the respective times for crossing. So to find the respective times for crossing, again, if we look here in my diagram, I can see again I have two horizontal lines and alternate angles. So therefore this angle up here in my diagram must also be the angle C. And respective crossing times means that I really need to find the velocity of B. So I need to use this right angle triangle, because if I can find the relative distance, then I can get the 45 meters. So if we draw a little diagram there, we have 45 meters across the stream. So if I can find the velocity in that direction, then I can use velocity is equal to distance over time. So let's just call this x here. C, we said, was going to be two different angles, and we have the velocity of the boat relative to the river was 3.2, and that was meters per second. So of course if I mark in there, that's the opposite and the hypotenuse. So I can use sine theta equals the opposite over the hypotenuse. And therefore I'm going to have two cases. So sine C, so when C is 39.48 degrees, and that's equal to the opposite, x over the hypotenuse, which is 3.2. So x is equal to 3.2 by sine 39.48 degrees. So therefore that gives me a speed of 2.035 meters per second straight across. And of course, velocity is equal to distance over time. So therefore the time will be the distance, which is 45 meters straight across, over the speed, which is 2.035. So the first time it takes to cross could be 22.1 seconds. Or we could, of course, have the second angle, which is 18.62 degrees over 3.2. And that gives me 3.2 by sine 18.62 degrees. And that gives us x is equal to 1.022 meters per second. And therefore the time would be 45 this time, divided by 1.022. So my second possible time for crossing would be 44.03 seconds. Okay. And I don't have marks for this one because it's 1998. Okay, sorry.